So let me show you before I go to the whole proposal, what Dean asked about. So this is we are testing 3 of those. Because we are testing mainly the bridge deck here. So we kept everything 8 inches, okay? And we are testing them in the new lab. I'll take you to the new lab too, okay? So we are testing simply supported one, about 6 feet, which is good number, 6 feet, okay? And where we are using here the BFRP, where deflection is not an issue. If deflection is an issue, I won't use it here. Okay, deflection is not an issue here, then we can use it here for the time being. Okay, so that's why exactly the same design. We're already doing a lot of things. We've been working on this one for years, you know. But right now we have the catch on it. What to do, what spacing we have to put in between in the wrong direction, what spacing. That's the main reinforcement. The black one is the main in the transverse direction. Okay. So we are testing them at 6 feet actually, not 6.5. And basically we have a bigger block, we anchor it down, and we get the steel thing, real steel thing. And instead of the studs here, we are putting bolts. Because I want to put the whole system down, lock it down here, and then once I finish testing, take it out and throw it away. Okay. So in between this one here and the beam, I put some kind of plastic things. I don't want to make it composite action. It doesn't help the purpose of the project, you know. Because I don't want to throw the beams, you know. I want to reuse them again.
Dr. Eason, so the deck is 8 inches by 9.6. How deep is it?
Oh, okay. The length of that one, we are looking what's called in bridge design as the strip width. The strip width, you know, in general design, about, in our thing, about 5 to 6 feet.
5, 6 feet?
Yeah, based on 6 feet spacing, depends on the spacing, the strip width is about 5 feet.
Okay.
But I want to make a column between 6.5, 8, and other things.
Ah.
What is the spacing on the rebar?
We are looking at so many, we are doing what's called parametric study. We are looking at number 6 at 4, number 6 at 6, number 6 at 8. It's not going to be after 8. I want to explain something, you know, what's the difference in design, complete, and speed. The problem we have is, that's the load, P, strain, or deflection or anything. Here is the strain on the steel. Okay. In general design, complete steel goes up like this. Then you have cracking load. And then the curve changes, becomes a non-linear portion. The stiffness decreases. So you have the change in the trend of the load deflection curve. In BFRP, in carbon fiber is like this, even better than this. So no issue, you know. So the issue with this material is in this area. Serviceability. That's the issue with this material. Usually we design based on ultimate condition. We design. Then we come back and check for serviceability. If we deal with the carbon fiber, fiberglass, aramid fiber, all these materials, we have bigger problem. Once the concrete cracks here, what do you have here? You get much higher strength. So you see in this area here, once the crack develops, the moment curvature relationship, directly you have a lot of rotation with no increase in the load. So you have big crack development. So the main thing to eliminate this one here. Okay? How to eliminate that one? You have to reduce the spacing. You have to put a lot of reinforcement there. You have to put a lot of reinforcement there. Okay. In real design, we put the percentage of steel below the raw balance, much below the raw balance condition. In here, you go about 4 or 5 times the balance condition to satisfy serviceability. This is the problem here. But the strength, oh, you have a lot of strength. But who cares here what's happening? We care here what's happening.
Are you gonna try pre-stressing it to increase that service load? Are you gonna
But
pre-stress
not in
it?
bridge decks, you don't do that.
You're not gonna do it?
Cast and brace, all cast and brace.
How about post-tension?
You don't really, it's costly.
Hmm.
It's a lot of money involved.
Hmm.
You know, it's very costly for tension.
Hmm. In theory, though, would it increase the serviceability load if you had it under tension?
Yeah, you can do that. It will help a lot. We did that on the ties,
Mm-hmm.
restricted concrete tie.
You just
I'm
don't
getting
think it's.
some money from the US Army, about 70K, 70 or 70K,
Mhm.
to make some restricted concrete ties.
Mhm.
Dr. Issa, are you gonna do any, statistical analysis on the coefficient of variation of the strength of the rebar? Or
Yeah.
do you wanna get that from the supplier?
No, we are doing that. We are doing that. We start testing.
His
Mark
last-
Levine, he sent me some,
Mhm.
about a few bars, you know, about 20, how many bars we got?
Like 30 bucks?
30 bars. We got number 5 very little, but we got number 6.
Yeah, you're gonna have to, you can probably do sections, okay? Common sections and then just pull them apart. You get a coefficient of variation of probably a couple percent, maybe higher. That's, you subtract, if you're gonna do a 3 sigma, you subtract 3 times that gives you the design stress strain that you wanna work with. That's 90.
Oh, that's not the issue, you know. Like for example, I am very good in carbon fiber. We did a lot of work in carbon fiber. Like the strength is about 650 KSR. 650. We designed for 550 KSR. There's what's called guaranteed strength.
Wow, that's pretty good.
Oh, yes, yes. Believe me, we did big projects. I am the one who introduced carbon fiber for the Tollway Authority, for the
Probably-
bridge rehabilitation.
You're probably log 5 in terms of having the right,
Yeah,
strength.
because the modulus for carbon fiber is 33,000 KSI. For steel is 29,000. So we don't have this problem here.
Okay.
Very strong.
Another question for you. How did you pick 20" by 8" as a tire contact? That seems pretty high to me.
Which one?
20" by 8" is the tire contact.
That's the AASHTO code.
Pardon me?
That's the AASHTO code. The AASHTO,
Yeah.
the American Association of Steel.
That would be a
State Highway.
gigantic earth mover or something like that.
Yeah, it goes like this.
Hold on for a
No, no, no.
Oh.
Oh, well.
Special walls.
I didn't do it.
No, this is irresolute, you know. That's the contact along the, in the wrong direction.
What kind of force is your load cell going to produce?
We put the whole contact there. We have these. We load the whole thing.
Yeah, the total pounds, how much load do you want to use?
Oh, depends what I'm going. We have what's called the service load. The service load for the tire contact is 16 kgs.
16,000 pounds.
Yeah. But this 16 is nothing. It won't crack.
I was gonna say, that's not, in that 160 inches, that's about, 100 PSI, 140 PSI, maybe, a little bit more than 100.
How do you make this calculation, D?
I
We don't do it
took
like that.
16,000 divided
No, we
by
don't do it like that.
160.
We took it as a load.
That's
We take it as a load applied in that area. The axle load. We don't take stress like that.
Okay.
We take the load and then after we put the load down there, we put the load down there and then we start, let me show you here. You see, we put the load here. See how it is? And this is for one simply supported here. That's the contact area here. So we start measuring where are the cables in here. We look at this guy here and this guy. This will be in compression, this will be in tension for some distance. Then it goes into tension. This one here for temperature and shrinkage reinforcement, and this one here in the wrong direction to distribute the load, the truck load. To distribute the truck load at the bottom of the step. So what we're trying to say here, both the top reinforcement and bottom reinforcement the same. Number 6 at 4, number 6 at 6. To control this serviceability issue down there. Strength wise is very strong, much stronger than steel. We are testing here, I will show you the testing. We are testing here, and we get on Mark Levine, we get about 171 KSI, 160 KSI, 156 KSI. I tested 3 of them. And we took them up to failure. But he sent me some data that he has 225 KSI. What the heck he got 225 KSI? Who tested for him to get 225 KSI? That's BS, you know. There's no way to have this one 225 KSI, no way. The best material so far I tested is the guy from Carbon 1. You remember Carbon 1? You were part of the team.
Yeah.
These guys have good materials.
In automotive work in Detroit, we use a 9 by 12 footprint for a regular tire, a truck tire. And we use 10,000 pounds as the load. That's basically for roads
Yeah.
in Michigan, okay? But it seems to work, and you're very close to that with your 9 by 20. And your
No, this is not the issue here. The issue here, we make it just to make it, when you talk about AASHTO code, you're doing bridges, we go with the bridge code, with the AASHTO code. Usually people test, they don't put that thing, they put something else. But I try to be with the code, you know. I teach bridges,
Will you
bridge 1 and bridge 2.
will your load cell take the load up to failure?
Yeah.
Okay.
We have,
That's the design law.
yeah.
Is there a factor of safety in that, or that you're looking for?
We don't look at, in bridges, there is no what's called factor of safety.
No?
Factor of safety is my mother's time.
Okay.
My mother way back, you know, in the 60s, 30s, 40s, we used to design everything based on factor of safety. Right now, everything is based on statistical evaluation, probability of failure. So everything is changed now. You know, even we used to rule the allowable stresses way back, then we load into load factor design, but right now we are into LRFT, load resistant factor design,
Gotcha.
in bridges and buildings too. We are into that one now.
Okay. I like the setup.
So that's the singly supported one. We have 3 of those. The problem here is Jerry, his company Construction Drive, they agreed to do these things for us. You know, I have the letter from them. Right now we don't know what to do. You know, take the letter to these guys. I know these guys, but you know how it is. Jerry is not there anymore. You know these guys. Actually, Jerry has a big job here at UIC to remodel our concrete lab, about 360K. Right now, you know. To remodel our lab for our undergraduate. He got the things. You know. So this is